Hey everyone, I've gotten quite a few questions over the past couple of days about how to visualize a comparison distribution when we're talking about t-tests, when we're talking about the t-distribution, because it is kind of a different mental exercise than the comparison distributions we were talking about when we were working with our z-scores. So I figured since several of you had this question, it'd be easier just to do a visual for you because I know a lot of you are visual learners. If you don't have this question and you totally understood how the book explained it and you are good to go, that is fine. You are not obligated to watch this mini lecture by any means. But for those of you who are having a problem conceptualizing how the comparison distribution for a t-test differs from those we've been talking about with our z-scores and our z-tests, this is for you. All right, so remember we did that exercise when we talked about this pretend math problem where we would calculate the means of means and we would put together a comparison distribution based on the means of means. And I showed you how to do that StatLab software where what we would see was if we continued collecting enough samples, the means of our samples would eventually kind of coalesce with the means of the population, and that whole procedure just kind of, that was a mental exercise more so than a calculation that you'd ever do. The same thing is true for the t-distribution or the comparison distribution that you're using with your t-tests. So we'll walk through this slowly. Keep in mind, at the end of the day, when you're talking about a paired samples t-test or a t-test for dependent means, or an independent samples t-test, what you're doing is looking at the differences between their means, right? If I want to compare the performance on a group of calculus students taking an 8 a.m. calculus class versus a 10 a.m. calculus class, you think this class is bad, try taking calculus at 8 in the morning. I did it. I do not recommend it. But ultimately, what am I going to be doing? I'm going to be looking at the differences. I'm going to be subtracting their scores, right? I'm going to subtract the average score of this class from the average score of this class to see if the time of day makes a difference in the average score. Same thing if I'm doing a pre-test, post-test. Your textbook used the example of like a marriage communication workshop. If I'm trying to evaluate if my workshop that happened here made a difference, I'm going to look at the difference of the pre-test scores and the post-test scores. I'm going to subtract this from this and see if I have a difference. So what we're doing with our comparison distribution for these is with both of these, we are working with a hypothetical comparison distribution where our mean difference is 0. I'm going to tell you what I mean by that. Now, neither of these are an actual comparison. Remember that. These are both these kind of imaginary straw men that we're setting up so that we have something to compare. So let's start with this example with the calculus class of, does the time of day make a difference? We're going to say that Professor Brown is teaching a calculus class at 8 a.m. and a calculus class at 10 a.m. And we want to see if time of day makes a difference. What we're doing in our comparison distribution is we're saying, if I had a population of 8 a.m. stats classes and a population of 10 a.m. stats classes, right? Like, let's say I could measure or calculus classes. Let's say I could measure everyone all over the world that's ever been taught. What I'm saying is I could draw, and I have them all listed out in these boxes. I could draw endless samples of, let's say I'm selecting 5 different 8 a.m. classes at a time and 5 different 10 a.m. classes at a time. Okay, I'm selecting 5 at a time. I'm calculating the mean of these 5. I'm calculating the mean of these 5, and I'm subtracting them. If these are the same, what I'm going to expect to see is those mean differences, right? So mean of this minus mean of this, okay? I'm taking this mean, and I'm subtracting them. And so what I'm going to say, actually, let me put this down here. So x bar minus x bar, remember that means mean. If these two groups have the same score, I'm going to expect these mean differences to continue to be over here pretty close to 0, okay? So maybe I take 5 more, and I average these 5. I take 5 more, I average these 5, and I do another subtraction. And this one's here. What I'm saying is my pretend hypothetical straw man comparison distribution for my null hypothesis, I'm going to expect if these populations are getting basically the same average scores, what that's going to mean mathematically is that these mean difference scores are going to continue to be clustering around 0 and ultimately are going to end up with a mean of 0. So when I'm doing my independent samples t-test, if I'm comparing a real life Professor Brown's 8 a.m. calculus class with 10 a.m. calculus class, what I'm going to be doing is, after I calculate my degrees of freedom and do all that, none of you have really emailed me with questions with that, so I'm going to assume that you got what the textbook was saying and how to do that calculation. Please let me know if you need me to do a step-by-step on that. But what I'm going to be saying is, okay, when I do my calculations to get my t-score between these two classes, is it also about 0? Or is maybe my t-score going to be landing somewhere over here that I'm going to be able to say, okay, my t-score is statistically significant from 0. There is a statistical significant difference between the scores of these two classes, meaning the time of day is making a difference. So again, my comparison distribution is not some population calculus score. My comparison distribution is a distribution of scores of mean differences. I'm trying to say that as clearly as possible. I'm hoping that makes sense. So let's move to another example. Let me erase these X's. Let's move to another example and talking about the pre-test, post-test. Let me get these off of here. Because again, for the paired samples, or the t-test of dependent means, we are continuing to work with a hypothetical population of a change of 0. Okay? So let's say that we are looking at, so your textbook used, if you can improve interpartner, I think they specifically used marriage, but if you can improve interpartner communication among men by doing a partner communication workshop. Okay? So again, remember, my null hypothesis that I'm comparing this to would be, like, let's say that this workshop was every Tuesday night for 3 months. My null hypothesis is going to be a comparison to partnered men within the general population that are showing no change in their partnered communication skills over this 3-month period, right? Some people might naturally get better at communicating over 3 months. Some people might have their communication levels decrease over 3 months, but we're assuming that that group, it averages out to 0, right? So what we're wanting to compare is within this 3 months, pre-test to post-test, doing this partner communication workshop, are we seeing an increase in their communication skills in a way that's statistically significant from 0? Because again, let's say I have 50 people in my workshop that I'm doing, and I go out into the general population and I survey these 50, and then I come back 3 months later and I survey these people, these 50, and I take their mean difference score, right? I subtract their pre-test score from their post-test score for all 50 of these people, and I take the mean of it. if there is no difference, I'm going to expect that mean to be pretty darn close to 0 over here. I do it again with another 50. I expect that mean to be pretty close to 0. I keep doing this with groups of 50 people within the population, and what I expect to see is if there is no change from the first part of this 3 months to the last part of this 3 months, the mean difference scores are going to continue to cluster around this 0 value, giving me a comparison distribution, my t comparison distribution of a normal distribution with a mean that continues to center around 0. This is my comparison distribution. So this is why my math can make sense if what I'm doing is, all right, I'm looking at person one's pre-test score and person two's post-test score, and I'm taking the difference. Or person one's pre-test and person one's post-test. I'm looking at person two's pre-test and person two's post-test and taking the difference. And on and on and on and on for all of my 50 participants that I have over here. I'm continuing to take their pre-test and their post-test and subtract them from each other. And then when I calculate the mean of all of those differences, I'm looking up here at my comparison of 0. If they only end up having a mean improvement of, I don't know, maybe 0.3 on a communication scale of 100, that's going to be pretty darn close to 0 over here, right? This is probably going to fall within this comparison distribution and be similar. And again, we would have to do our degrees of freedom and actually do our math to determine that. I'm just throwing a number out there. But let's say we see their average communication improve 18 points on a 100-point scale. There's a good chance that those 18 points are probably going to land them somewhere over here. And we can say, okay, so this group has a difference score that is statistically significantly different from this comparison population distribution where the mean difference scores are going to continuously center around a mean difference score of 0. I hope that has clarified things and not confused you further. But this goes back to the foundational logic of what we're doing with t-tests and how we're making these comparisons, as well as why it makes sense to be doing a comparison distribution, a t-distribution that always has a mean of 0 versus a population distribution like what we've been talking about with our z-scores. If that did not help at all and you still have questions, feel free to email me.